So in this lesson, we will learn about chemical equilibrium. First, let me tell you about equilibrium. In this word, you hear the word equal. So in this system, this is equilibrium vapor pressure, just to demonstrate the word equilibrium. As the liquid turns into gas, and this is a sealed container, if this is a certain temperature, let's say 25 degrees Celsius, and that's not changing, some of the particles will be in the gas phase, some will be in the liquid phase. When it reaches equilibrium, you will have 1, 2, 3, 4, 5, 6, and you'll have 14 in the liquid phase, and that number will never ever change. If the numbers of the gas is 6 and the liquid is 14 and it does not change anymore, you have reached equilibrium. Now, it doesn't mean that those two numbers are equal. It means that the molecule turning from liquid to gas, the rate of that happening is the same as the rate of the gas turning into liquid. So in other words, it's not stagnant like this. It's always moving back and forth. But if a liquid turns into a gas, one of the gas molecules have to turn into a liquid. At all times, there will be 6 here and 14 here, not the same 6 molecules, but 6 molecules total. Okay, that is true equilibrium. Now, in a chemical equilibrium, you have now chemicals. Like this is N2O4 is a chemical. This is N. This is N, O, and O. Okay, N2O4 is a colorless gas right here. You can see that in that tube. Okay, now N2O4 in this tube is at equilibrium with NO2. NO2 is a brown gas. NO2 is responsible for acid rain. So if you have NO2 gas in the atmosphere due to the combustion of nitrogen, so you have nitrogen plus oxygen, you're going to have NO2 after you balance it. So that's going to be pollution in the air and it's brown. And if you add water to that when it rains, you're going to get nitric acid. Okay, so you can see that brown. So these two are at equilibrium. And as you can see, it breaks in the middle like this, and you have 2 NO2s. So those two are always at equilibriums. Okay, so if I had counted 10 over here, and 2 inside of 2 in here inside this container, let's say, and those numbers are not changing, you are now at equilibrium. Now there is something called equilibrium constant. Equilibrium constant is what chemists use to see how far along the reaction has occurred. For example, in this reaction, you have 10 products to 2 reactants. We always put the products on top because we're always interested in how much we produced, because let's say we have a factory making NO2, we want to be considering how much money we'll make if we make those products. So when the reaction is done, you will make 10 to 2, and the ratio is the same as 5 to 1. Or the equilibrium constant, they call it, is equal to 5. Okay, the bigger the number is, it means the more products you'll make. Okay, so the equilibrium constant tells you the extent to which the reaction occurs. More on that later. This is just a brief overview. You will see the reaction sometimes written with a double-headed arrow, and sometimes I leave it out because it's hard to type it in the computer. So that is at equilibrium. That means there are 2 rates happening here at equilibrium. The forward rate with the rate constant of Kf for forward, and the reverse rate with a rate constant of K reverse. Okay, so as N2O4 turns into NO2, NO2 turns into N2O4. Look at this graph and tell me what's happening to the rate. Okay, so the rate increases and reaches a flat line. Here the rate increases and reaches a flat line. As soon as they're flat line, that means you have reached something called equilibrium. Okay, at equilibrium, the rates are equal. Not the amount of N2 to N2 and N2O4, the rates are equal. One goes up, the same rate as the one goes down. Okay? Remember, in this plot, they're plotting the rate on the y-axis, as it's different from this plot. Now look at this plot. They're plotting concentration. Pause your video and look at how different the graph is. This graph is showing you now the amounts. So here you can see the amounts at equilibrium. They may not be equal, but they are constant. It's always 10, it's always 2. Of course, at a certain temperature, you can't change that temperature. Okay, so here you can see if N2O4, it's up here, of course it's going to turn into NO2, right? So it's the concentration of it, the molarity, moles over liter, is going down until it flatlines. Okay, the NO2 is being produced, so you're making more of it until it flatlines. When it flatlines, you have achieved equilibrium. Okay, that's how you know. The concentrations are written here. This might be 10 molar. This might be 2 molar. Even though they're not equal, they're still at equilibrium because the rates are equal, not the concentration. Okay, it says once equilibrium is achieved, the concentration of each product are constant. It's no longer changing, it's flat lines. Okay, since in a system at equilibrium, both the forward and reverse reactions are being carried out, we use a double arrow written here.